Yes, you read the essential question correctly. How do you use Hero's formula to find the area of a triangle? And yes, you read it correctly. How do you find Brahma Gupta's formula to find the area of a cyclic quadrilateral? I'm going to show you in a short little video how it works. Now, behind me, you're going to see a triangle. You see one side length is 5, one's 6, one's 9. The question is to find the area of the triangle. Well, here's the thing. We've done tons of questions with triangles and finding the area of it. The problem with this one is this. If you look at it, nope, it's not a regular triangle. All the sides aren't the same. Oh, which means nope, it's not an equilateral triangle, so I can't use that formula. Nope, it's not a right triangle. There's no right angles given. In fact, if you did the Pythagorean theorem, you'd find out it doesn't satisfy it, so therefore it's not a right triangle. Darn. Nope, it's not a 30, 60, 90 triangle. It's not in the ratio of x, x root 3, and 2x. Next one. Nope, it's not a 45, 45, 90 triangle. It's not in the ratio of x, x, and x root 2. Oh, I got it. Why don't we do this? Let's draw an altitude. Well, we can draw an altitude, but oh no, it doesn't help us. Because yes, this determines the base, but there is no way for me to find the length of that altitude. So it's not going to work. The only thing I can do is find the perimeter. I can take 5 plus 6 plus 9, which would give me 20. Oh, I'm going to teach you something because we're going to use this in a little bit. There's also something called a semi-perimeter, which is basically, as you see, it's just half of whatever the perimeter is. Now, the only way that we can find the area of this triangle is, ladies and gentlemen, we need a hero. I need a hero! Oh, I'm not going to sing the rest of it. I know that was very good, but we need a hero, and here we go. Here comes the hero. Theorem 111. It is Hero's formula, by the way. Yes, back 2,000 years ago, a guy named Hero of Alexandria came up with this particular formula, and it does work, to find the area of a triangle. If you're given 3 side lengths of the triangle, like I just said in that example, here is your formula. You need to write this bad boy down. You take the square root of the semi-perimeter, that's what S stands for, the semi-perimeter times semi-perimeter minus 1 side length, semi-perimeter minus 2nd side length, semi-perimeter minus 3rd side length. So you find numbers, plug them all in. Once you plug in all the numbers, simplify it out, and you're actually going to get your answer. So let me show you how you apply Hero's formula to this example that we just had. So back to the example, it looked like this. So 5, 6, and 9 were the 3 side lengths of the triangle. When I take Hero's formula and plug all this stuff in there, the first thing I've got to find is the semi-perimeter. Well, I did that right here for you. The semi-perimeter is just add them all up and divide by 2. So 10 is my semi-perimeter. Wonderful. So I put 10 in all for the S's. Great. 10, 10, 10, 10. And then one side length is 5. I put it in here. The other side length 6 is B. The other side length is 9, so I put that in for C. It doesn't matter what you put in order-wise for A, B, and C as long as you take the 3 side lengths. So when I simplify this out, guys, I get 10 here. 10 minus 5 is a 5. 10 minus 6 is a 4. 10 minus 9 is a 1. Woohoo! So I keep simplifying underneath the square root. I multiply 10 times 5 times 4 times 1, which gives me square root of 200. And then I can break up the 200. Remember now, I want to break that up into 2 factors where one of them is perfect. So 100 is a perfect square. So it's in jail. Since it becomes perfect, it comes out of jail, and it loses the jail cell. Woo! So the radical's gone, because the square root of 100 is just 10. So this is my final answer. There you go. I know it's weird. It's so strange. Hero, they were so genius people. They were such geniuses back in the day. It's crazy. So 10 root 2 units squared is the area of that particular triangle. So that's how you apply Hero's formula. Welcome. Good job. Moving on. Here we go. Look at this. Oh, it's a circle with a quadrilateral in it. And you see the question. What's the area of quadrilateral MASH? Well, you might say, well, look at that. It looks like a kite. Is it a kite? And I can use 1/2 diagonal 1 times diagonal 2? Nope. Not a kite. Oh, I got it. Maybe it's a rhombus. I can use this formula. Base times height. Nope, not a rhombus. Oh, I know. It's a trapezoid. Nope. Can't use a trapezoid formula. Cannot use 1/2 height times the sum of the 2 bases. That one doesn't work. Oh, I got it. Why don't we draw AH here to here, like that, and create 2 triangles and find the area of that? Wonderful idea. Good thinking. Problem is, nope. Doesn't work. There is no way to find the area of these two triangles. So what we're going to have to do is use a different formula. Now I'm going to teach you something here quick. This is a definition you need to know. This is a special one because this quadrilateral right here, MASH, is what we call a cyclic quadrilateral. It is a quadrilateral that is inscribed in a circle. And remember, inscribed means that each of the vertices of the polygon is actually on the rim of the circle. So that's a cyclic quadrilateral. And if you look, we have to go way back. Approximately 1400 years ago, there was a Hindu mathematician, that's right, named Brahma Gupta. Sounds like a cool name. Now you think his buddies called him like, seriously, Brahma Gupta, what a name. Like, you gotta give him a nickname. So what would it be? Like, Yo Bra? Would it be Ma? Would it be Goop? I bet that's what it was. I bet it was Goop. I bet they called him the Goopster. Yo Goopster! What's up, Goopster? Just hanging out like a rock, something, just chilling. Like, what's up, guys? And he says, yeah, I got this cool formula. I think it's going to work for cyclic quadrilaterals. And they said, Goopster, you're a genius. I don't know. I think that's probably how it went down. But here you go. Here is Brahma Gupta's formula to figure out these cyclic quadrilaterals in terms of their areas. It is Theorem 112. And here it is. Brahma Gupta's formula for cyclic quadrilaterals. It looks very similar to Hero's formula. Maybe they were brothers. Not even close, because they were 600 years apart. Get with it. Maybe the same family tree. Who knows? The Gupster and Hero. Tight. So this is it. The square root. Oh my. The square root of S, which again stands for semi-perimeter, minus the side length, semi-perimeter minus another one. You get the idea. So all you got to do is plug in the numbers and calculate it properly, and you will have your answer. So let's do this example. Back to the cyclic quadrilateral that I started with. You have one side length of 5, another one's 5, another one's 9, and another one's 3. Well, first you got to start with the semi-perimeter. So we find the semi-perimeter right here, add all the numbers together, divide by 2, gives you 11, so that's your semi-perimeter. So anywhere you see the S, bam, 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 11, 11, 11, 11. That's where they go. And then just take the 4 side lengths and plug them in for the A. So 5 goes there, this 5 goes there, this one side length 9 goes there, this other side length, the remaining one, goes here. Again, it doesn't matter the A, B, C, and D. You can switch the 9 and the 3 if you want to. It doesn't matter. So we just, parentheses first according to my order of operations. 11 minus 5 is 6. 11 minus 5 is 6. 11 minus 9 is 2. 11 minus 3 is 8. Multiply all that together. 6 times 6 times 2 times 8 gives you 576. And believe it or not, the square root of 576 is a nice number. That's already a perfect number. So it's out of jail. And the answer is 24 units squared. Congratulations. There's your first of many examples using the Gupster's formula. That's practice. Later.